Welcome back, everyone. In today's lesson, we are going to look at spanning tree protocol concepts. Firstly, let's look at the purpose of STP. Redundancy is an important part of the hierarchical design for eliminating single points of failure and preventing disruption of network services to users. Having alternate physical paths for data to traverse the network makes it possible for users to access network resources despite path disruption. However, redundant paths in a switched Ethernet network may cause both physical and logical layer 2 loops. Ethernet LAN requires a loop-free topology with a single path between any two devices. A loop in an Ethernet LAN can cause continued propagation of Ethernet frames until a link is disrupted and breaks the loop. Let's look at this for an example. As you all might know, a switch is gossip central. When it gets a broadcast, it will broadcast to everyone within its range. And it's usual for a switch that when it gets a broadcast, it will forward it to everyone except from the interface where it got the broadcast from. So if I were to put that in an analogy, it's like A, B, and C are friends. B has a rumor and B tells A about the rumor. A knows the rumor now and wants to spread the rumor, and then A tells C. A does not tell B about the rumor because B already knows about the rumor. Once A tells C, C thinks, oh, B doesn't know. C will tell B. So it's sort of like moving around this rumor from people to people. The analogy is very similar here. Let's look at this example. We have a topology with three switches here. I've named the switches Nemo, Coco, and Shrek. Okay? And each switch has a priority and a MAC address. Let's say PC1 sends a broadcast frame. So Nemo gets the broadcast frame. Nemo will then forward the broadcast frame to Shrek and Coco. When Coco receives the broadcast frame from Nemo, it will forward the broadcast frame to Shrek, but not to Nemo, because Nemo was the source. The same goes with Shrek. When Shrek received the broadcast from Nemo, it will not forward it back to Nemo, but it will forward to Coco. Now Coco, when he gets the broadcast from Shrek, he now forwards that broadcast to Nemo, but doesn't forward that broadcast to Shrek. Same goes, Shrek will forward the broadcast he got from Coco to Nemo. And then Nemo, getting this, will forward it again. So can you see how the forwarding of this broadcast is going around and around and around in that particular topology? While this topology has redundancy, that redundancy has led to a loop. And this loop is not a good thing to have in your network. Spanning tree protocol is a loop prevention network protocol that allows for redundancy while creating a loop-free layer 2 topology. STP logically blocks physical loops in a layer 2 network, preventing frames from circling the network forever. In this example, this particular link from S2 to S3 has been blocked. The packets can traverse through other lines to get to the destination, but this path, although physically is still available, logically it is blocked. What it does is that it now will not accept any frames that comes through this because it is now a blocked path. So this way, STP has cut down on the loop and it can provide loop prevention. This link was blocked just now. So let's say that this link is down. Because this link is physically available, it will now be unblocked and then it will now work as usual. So STP compensates for a failure in the network by recalculating and opening up previously blocked ports. Let's discuss issues with redundant switch links. Path redundancy provides multiple network services by eliminating the possibility of a single point of failure. When multiple paths exist between two devices on an Ethernet network and there is no spanning tree implementation on the switches, a layer 2 loop occurs. A layer 2 loop can result in MAC address table instability, link saturation, and high CPU utilization on switches and end devices, resulting in the network becoming unusable. MAC address table instability happens when every time there is a new frame coming in with a new source port, and that will keep updating the MAC address table and it never reaches stability. Link saturation happens when all this broadcast frame is running around in the network using the bandwidth. The real packet for real work cannot really use the link. Layer 2 Ethernet does not include a mechanism to recognize and eliminate endlessly looping frames. This is different from Layer 3 devices. So both IP version 4 and IP version 6 include a mechanism that limits the number of times a Layer 3 networking device can retransmit a packet. A router will decrement the time to live in every IP version 4 packet and the hop limit field in every IP version 6 packet. When these fields are decremented to 0, the router will drop the packet. Ethernet and Ethernet switches have no comparable mechanism for limiting the number of times a switch retransmits a Layer 2 frame. STP was developed specifically as a loop prevention mechanism for Layer 2 Ethernet. Without STP enabled, Layer 2 loops can form, causing broadcast, multicast, and unknown unicast frame to loop endlessly. This can bring down a network quickly. When a loop occurs, the MAC address table on a switch will constantly change with the updates from the broadcast frames, which results in MAC database instability. This can cause high CPU utilization, which makes the switch unable to forward frames. An unknown unicast frame is when the switch does not have the destination MAC address in its MAC address table and must forward the frame out all the ports except the ingress port. Broadcast storm is an abnormally high number of broadcasts overwhelming the network during a specific amount of time. Broadcast storms can disable the network within seconds by overwhelming the switches and end devices. Broadcast storms can be caused by a hardware problem such as a faulty NIC or from a Layer 2 loop in the network. Layer 2 broadcasts in a network such as ARP requests are very common. Layer 2 multicasts are typically forwarded the same way as a broadcast by the switch. IP version 6 packets never forward a Layer 2 broadcast, but ICMP version 6 neighbor discovery uses Layer 2 multicasts. A host caught in a Layer 2 loop is not accessible to other hosts on the network. Additionally, due to the constant changes in its MAC address table, the switch does not know out of which interface or which port to forward the unicast frames. To prevent these issues from occurring in a redundant network, some type of spanning tree must be enabled on the switches. Spanning tree is enabled by default on Cisco switches to prevent Layer 2 loops from occurring. The spanning tree algorithm was invented by Radia Perman in 1985. Her spanning tree algorithm creates a loop-free topology by selecting a single root bridge where all the other switches determine a single least cost path. STP prevents loops from occurring by configuring a loop-free path through the network using strategically placed blocking state ports. The switches running STP are able to compensate for failures by dynamically unblocking the previously blocked ports and permitting traffic to traverse the alternate path. So how does the spanning tree algorithm create a loop-free topology? It does this by first selecting a root bridge. The root bridge or the switch is the reference point for the entire network to build a spanning tree around. After it has the root bridge, it will now block redundant paths. STP ensures that there is only one logical path between all destinations on the network by intentionally blocking redundant paths that could cause a loop. When a port is blocked, user data is prevented from entering or leaving that port. And then it creates a loop-free topology. A blocked port has the effect of making that link a non-forwarding link between the two switches. This creates a topology where each switch has only one single path to the root bridge, similar to the branches of a tree that connect to the root of the tree. Recalculate in case of link failure. Links go up and down, so the physical path still exists to provide redundancy, but these paths are disabled to prevent the loops from occurring. If the path is ever needed to compensate for a network cable or switch failure, STP recalculates the path and unblocks the necessary ports to allow the redundant path to become active. STP recalculations can also occur anytime a new switch or new inter-switch link is added to the network. Here I'm going to show you a rough example of how root bridge selection is done and how redundant path is blocked. Again, we have a topology with three switches, Nemo, Coco, and Shrek. Nemo has the priority of 1, so does Coco, so does Shrek. And this is the MAC address simplified for Nemo, Coco, and Shrek. Now, when a root bridge is going to be selected, it goes by the bridge ID. And bridge ID is set by the priority and the MAC address. The lower the priority, the higher the chances to become the root bridge. The lower the MAC address, the higher the chances to become the root bridge. So let's say between here we have cost. Okay, this is 4, between Coco and Shrek is 3, between Nemo and Shrek is also 3. In the beginning, all the switches would advertise themselves as the root bridge. So here you have Nemo saying, I am the root bridge, the cost is 0 because the cost to himself is 0 from himself. From Nemo to Nemo is 0. Okay? And then he will send this to both Coco and Shrek. Coco and Shrek does the same thing. Shrek will say, I am the RB, I am the root bridge, and my cost is 0, and sends it to Nemo and also to Coco, and Coco does the same. Let's say Nemo gets the message from Shrek. He looks at Shrek and says, priority, same as mine. MAC address, I am lower, so I am still the root bridge, and the cost is 0. Meaning that Nemo does not change who the root bridge is because the option given by Shrek is not as good as his own option. When Coco receives the message from Nemo, this message, when Coco received that, he will check and see, oh, priority is 1, the same as mine, but Nemo has the lower MAC address. So Nemo is a better candidate for a root bridge. So now Coco says Nemo is the root bridge and the cost is 4, meaning from Coco to Nemo, the cost is 4. Shrek, receiving the same information from Nemo, would check as well. Priority is the same, but Nemo's MAC address is lower. I agree that Nemo is the root bridge and cost to Nemo is 3. This message here from Coco will be sent to Shrek, and from Shrek will be sent to Coco, and they would agree that yes, Nemo is the root bridge and the cost is set accordingly. So now everyone agreed that Nemo is the root bridge. So how about the blocked path? The path that is in play right now is to find out how each switch can get to the root bridge. So the best way for Coco to get to Nemo is directly from Coco to Nemo because the cost is 4. If Coco goes from Shrek to Nemo, the cost is 6. The cost is higher, so he doesn't take that one. So he chooses this path. Same goes for Shrek. Directly connected to the root bridge, the cost is 3. If he goes via Coco, the cost would be 7. So he will use this path. So this path over here, this redundant path, right now has no value. So this path will be blocked. So even though this path is blocked, all the packets can still traverse the network. From PC2 can go to here and get to there. From PC2 can go to Nemo to get to PC1. So there is no real use of this particular path. Now let's say as the network goes on, suddenly this path from Nemo to Shrek is down. So then it will recalculate this one and update this block path to unblock it. So that is a simple view on selecting a root bridge and blocking redundant path. In this lesson, we looked at the purpose of STP. Why do we need STP? And then we looked at an overview of how selections can be done. In the next lesson, we will focus more on electing the root bridge and also blocking path, recalculating, and so on. So until the next lesson, goodbye.